Chapter 19, Problem 9. Draw the d orbital diagrams according to the crystal field model in order to predict how many unpaired electrons are in each of the following. So first we want to address what does it mean by the crystal field model. So this is a model that explains the energy gap between the d orbitals due to the presence of the ligands. So on the left here, we are looking at an octahedral splitting pattern. So the top two d orbitals, which is easier to see in the right graph, the z squared and the x squared minus y squared, these are right up close to the ligands. So if they're close to the ligands, that means they're going to have maximum repulsion. More repulsion means higher in energy. So two of the d orbitals are right next to the ligands, but then the bottom three orbitals, the xy, the yz, and the xe, they're just kind of near the ligands. So these are not as close. And if they're not as close, they can't be experiencing as much repulsion. So their energy isn't as high. So we call this graph on the right an octahedral splitting pattern. Now, for octahedral, there's two ways to fill. There's low spin and high spin. The spin is going to be dependent upon the type of ligand that is on our transition metal. So if we look at the formula for A, it's cyanide. And then if you go down to the bottom here in this gray box, we get what's called the spectrochemical series. And it puts the ligands in order of their strength to the metal. Now, if it's stronger, it's going to cause a larger delta between the energy of the orbitals. So cyanide is the one in this particular problem. And we can see out of all of these, it's going to have the largest delta. So if you have this really large delta, the electrons would actually prefer to stay in the low orbitals, the xy, yz, and xe, because it is going to take energy for them to jump up into the z squared or x squared minus y squared. So we're going to keep all of the electrons in the low orbitals. Now, low spin does not mean low orbitals, but it just so happens they go together. So low spin, stay in the low orbitals. All right, so now we need to know how many electrons are we going to put into this splitting pattern. So if we go over to our formula, cyanide is -1. So we have 6 negative ones, but the total on this is -3. So the only way that could be true is if the iron was +3. So now if we go look at the periodic table, an iron with a +3 charge has an electron configuration of argon 3d5. So if I put my 5d electrons in and I stay in the low orbitals, I'm going to do 1, 2, 3, 4, 5. So that turns out that there's only one unpaired electron, which is ultimately what the question asked us to do. Now, if we were able to utilize the upper or high orbitals, those 5 electrons would all be in separate orbitals. So you would have more unpaired electrons because they would all be individuals. Okay, let's try B. So for B, we've got, again, an octahedral complex ion, and therefore it should have the same pattern as the one before. But now the ligand is bromide. So if we look at our spectrochemical series, bromide is all the way on the right. So we're looking at a small change in energy between the d orbitals. So if it's small, that means that it doesn't take a lot of energy for it to jump up into that high d orbital. And so it would rather spread out and use all of the orbitals. So in the case of a small delta E, you're going to notice a high spin or utilizing the high orbitals. Now bromide is -1. So we have 6 -1s and a net charge of -4. So the cobalt has to be +2. So cobalt +2 has an electron configuration of argon 3d7. So if we could use the high orbitals, we're going to go 1, 2, 3, 4, 5, 6, 7. So that results in 3 unpaired electrons. So if this was low spin, right, we would completely fill the bottom before we attempted to put any electrons in the top. All right, part C. Now we're looking at a tetrahedral. It's a totally different shape. So where the ligands are with respect to the d orbitals is not the same. So with tetrahedral, it's harder to see it. So I'm not even going to try to look at those graphs. Instead, I'm just going to focus on the splitting pattern. So the first thing we should note is that it's the opposite pattern. We're seeing that X, Y, Y, Z, X, Z are all on the higher energy level. So that must mean those orbitals now are closer to the ligands, but the Z squared and X squared minus Y squared are a little bit further apart. The thing about tetrahedral, though, is the delta is always small, no matter what. So for all of the ligands, even though some are bigger than others, none of them are big enough to change how it fills. So tetrahedral can only fill with a high spin. Regardless of the ligands, it's always high spin. So ethylene diamine, this is a neutral ligand. So since the total is +3, the manganese has to be +3. If you look on the periodic table, manganese +3 is argon 3d4. So if we're going to put 4 electrons in at a high spin filling, we're going to use 4 separate orbitals and therefore have 4 unpaired electrons.